Hello everyone, my name is Rezvan Joshaghani from Boise State University. Today I'll be presenting our work titled XR Module for Enhancing Glove Hygiene Skills in First Year Chemistry Laboratories. This work was conducted in collaboration with Alessandra, Yanyan, Zong, Stephen Cutchin, and was supported by National Science Foundation. In this study, we examined whether immersive XR can improve a students' emotional readiness for their first university chemistry lab experience. First-year chemistry laboratories are high-stakes environments. Many students enter university with limited prior lab experience. They may never have handled lab equipment, worn proper PPE, or worked in safety-critical settings. This lack of familiarity often produces anticipatory anxiety, and anxiety is not trivial. It consumes working memory, reduces engagement, and can undermine performance. Importantly, this anxiety disproportionately affects the student from under-resourced schools or those without prior laboratory exposure. So our central question was, can immersive XR improve the student affective readiness before they enter physical lab? That's where XR comes in. Immersive technology is compelling here not because it's novel, but because it allows the students to practice in a psychologically safe environment where mistakes carry no real consequences. The theory behind this is important. Control value theory tells us that anxiety is closely tied to perceived control. If students become more familiar with the procedures and the environment, the perceived threat should decrease. The cognitive affective model of immersive learning, or CAML, suggests that core affordance of VR, such as presence and agency, directly influence emotional states like anxiety. At the same time, anxiety and confidence are driven by different mechanisms. According to social cognitive theory, self-efficacy emerges through repeated successful performance and feedback, not through one-time experience. So going into this study, we expected immersive VR to influence anxiety. We did not necessarily expect it to shift self-efficacy. And that distinction turned out to be central to our findings. Our work builds on prior XR-based laboratory safety research, particularly the glove hygiene module developed by Breuer et al. Their VR system effectively visualized contamination pathways and demonstrated procedural value in introductory chemistry. More broadly, XR has been used in chemistry and laboratory education to increase engagement, support the skill transfer, and replicate elements of hands-on training. However, most of this work has been focused on procedural accuracy or motivation rather than effective outcomes such as anxiety and emotional readiness. In addition, immersive VR is rarely compared directly to lower immersion alternatives, and scalability is often left unexamined. Our study extends this literature by focusing explicitly on affective impact, comparing immersive VR to both browser-based and traditional formats, and evaluating outcomes across multiple time points. Our paper makes three primary contributions. First, we find that immersive VR significantly reduces lab-related anxiety, outperforming both a browser-based simulation and a traditional multimedia worksheet. Second, we show that brief VR exposure does not significantly shift self-efficacy. We argue that this is not simply a null result, but a theoretically coherent distinction between emotional regulation and mastery-based confidence. Third, we demonstrate a dual deployment model, offering both an immersive VR experience and a browser-based alternative, making this type of intervention scalable and accessible. Let's walk through the module briefly. This system builds on glove hygiene simulation developed by Breuer et al., which introduced contamination tracking in an immersive chemistry lab. We extended that work and incorporated it into our experimental design. The virtual lab, built in Unity, mirrors the physical lab students later enter. Students move through the realistic glove hygiene workflow, putting on PPE, setting up titanation, and handling chemical solutions. Throughout the procedure, we introduce common interruptions, a phone call, a coffee break, a printer jam, the kinds of moments where students may forget they are wearing contaminated gloves. These interruptions are intentional because they reflect real lab conditions and allow us to observe how students manage contamination under distraction. At the end, the students trigger a contamination replay that highlights every surface they touched. This makes invisible hazards visible and reinforced behavioral consequences of improper glove use. One thing we cared about was accessibility. Not every student can use VR headsets, whether due to motion sickness, disability, or simply not having access. So we deployed a module in two formats, an immersive version on MetaQuest 3 using Unity XR Interaction Toolkit with teleport-based locomotion, and the browser-based WebGL version that preserves the core training functionality, but works with just keyboard and mouse. The control group received a more traditional package, an instructional video, a podcast, and a reflective worksheet. These three condition designs allow us to isolate effects of immersion from the instructional content itself. We ran three armed randomized experiments with 176 undergraduate students in an introductory chemistry course at the University of Southern California. The sample was predominantly first year, predominantly female, and racially diverse. The timeline is important. Students completed a baseline survey at T1, but then they randomly assigned to one of three conditions. They completed their training within 1 week, about 15 to 20 minutes. Then we surveyed them again at T2 after training, but before their first real lab. And then again at T3 after they completed their first in-person lab session. This three-time point design lets us distinguish between immediate effect of training and what persists after real-world exposure. We measured two primary outcomes. Lab anxiety was captured with a 4-item adapted scale, including items such as I am very nervous about the upcoming chemistry lab, using a 7-point Likert scale. Reliability was strong across all time points, with alpha ranging from 0.84 to 0.91. Self-efficacy was measured with a 9-item scale assessing perceived competence and confidence in lab tasks, also with high reliability, with alpha ranging from 0.91 to 0.93. We controlled for prior lab exposure, gender, socioeconomic background, first-generation status, and race and ethnicity. This allowed us to isolate training effect from pre-existing differences. You can see the bar chart on the right at T2 after training, but before the real lab, the VR group reported significantly lower anxiety than both the web-based and control group. The effect size were medium, with the around 0.5 compared to web and 0.19 compared to control. At T3, after the first lab, something interesting happens. The VR advantage over the web group actually grows, with D equal to 0.71, while the control group anxiety dropped and converged with VR. The real lab experience itself acted as an equalizer for the control group. The web-based group, however, showed a slight increase in anxiety after the real lab. That is a meaningful signal. Simply presenting procedural content on a screen does not prepare students emotionally in the same way that immersive rehearsal does. The bottom line is that VR reduces anticipatory lab anxiety, and that effect was durable. Now, on the other side of the coin, when we look at self-efficacy, which reflects the students' confidence in their ability to succeed in the lab, we see no significant difference across groups at either T2 or T3. The effect size are small, around 0.2 to 0.3, and none are statistically significant. This is not disappointing finding. It is consistent with theoretical expectations. Self-efficacy is more stable and develops through repeated mastery experiences and performance feedback. A single 15-minute module on glove hygiene, however immersed, was unlikely to shift the students' broader sense of lab competence. What it did shift was their emotional state, and that distinction is central to our findings. The dissociation between anxiety and self-efficacy is not just a statistical pattern. It aligns closely with established learning frameworks. Anxiety is a state-level emotion shaped by perceived control. When students rehearse laboratory procedures in VR, they develop procedural familiarity and a clear mental map of the environment. That increased predictability reduced the threat, consistent with control value theory. Self-efficacy operates differently. It depends on evidence of successful task execution through repeated mastery and performance feedback, which a brief procedural simulation cannot fully provide. The Camel framework anticipates this distinction. It suggests that psychological affordance of immersion, such as presence and agency, are most directly influence affective states than confidence beliefs. This is precisely the pattern our data reveals. So what does this mean for practice? If your goal is to reduce pre-lab anxiety, especially for underprepared or first-generation students, a short XR intervention is a cost-effective and a scalable solution. A brief immersive experience can recalibrate emotional readiness. If your goal is to build self-efficacy, you will need something more. That requires repeated practice, progressive difficulty, performance feedback, and longer-term engagement. XR functions as a low-dose emotional scaffolding. It prepares the students to engage, even if it does not yet strengthen broader competence beliefs. With a blended instructional model, that role is highly valuable. We want to be transparent about limitations. Our outcomes rely on self-reported measures with a strong reliability, but they may not fully capture behavioral readiness. The sample comes from a single institution and one course, so generalizability requires further testing. Although the system tracked contamination events, those behavioral logs were not modeled as performance metrics in this analysis. Going forward, we plan to integrate objective behavioral measures such as contamination frequency and error recovery patterns, and link them to effective outcomes. We also aim to conduct longitudinal studies across multiple semesters to examine whether repeated XR exposure can influence self-efficacy trajectories, and whether effective gains translate into improved retention and performance in STEM courses. To wrap up, immersive XR pre-lab training significantly reduces anticipatory anxiety for first-year chemistry students. It is scalable across both immersive and browser-based delivery formats. It strengthens affective readiness, which forms an emotional foundation for effective hand-on learning. Anxiety and confidence follow different mechanisms, and our study provides empirical evidence for that distinction. Thank you for watching. We hope this work clarifies how immersive XR can strengthen effective readiness in STEM education.